So, welcome to this lecture on remote sensing, digital image analysis, classification, and evaluation. So, how do we classify an image, as in determine what's actually in it, what's being shown in this image, and then evaluate this classification. So, we'll start with the classification to begin with, and we of course are going to be able to divide this up into lots of different ways, lots of different categories. That's what we like to do. But we can start with an initial division of human and machine. Most of this lecture is going to be about the machine, although you are always there helping it, having to do a lot of the work. But the initial analysis, as a human, we can look at an image and go, well, that looks like a field, that area over there. Let's say we can draw a line around this field here, and we can draw a line around the woodlands here. And this is what happened before we had access to computers. We would look at an aerial photograph and sit there behind a strange machine, staring into the machine and draw lines around objects. That was how we classified an image. That was fine. We could use our brains for doing this classification, interpretation of what's in the image, the textures and the colors that are there that inform us, that give us clues. And we can use that information, the contextual information and the textural information that's there to make those decisions. The computer, though, has a harder time. Computers are fast, but as I mentioned before, they're quite dumb. Which is, I don't want to be too critical of them. They're quite helpful. But the computer analyzes essentially pixel by pixel. There are modern algorithms for assessing areas, looking for objects in an image, but even that process begins by doing an analysis on the color of each individual pixel. When I say color, I mean the spectral signature, the light that's being emitted in all wavelengths, or the measured wavelengths at least, from that particular pixel. So what we're going to be looking at here in this lecture are the pixel-based processes. We won't be looking at the slightly more modern algorithms that look for areas and objects within the image. So we are attempting here with this classification, or with this with classification, to create information classes. We want to make a map of, say, vegetation cover, or of rock type, the geology, or the soil type. So we have these different things. We want to create a thematic map where we have categories of different things that might exist in this image. But to get there, we are going to have to go via some form of spectral class. We want information classes, but we have to go via the spectral class. What does this mean? Well, we have our information classes. We've mentioned this before, an information class being a class of pixel or thing in our GIS, whatever it is, that has information beyond the apparent in say the aerial image or the satellite image, so that we can say that it is a type of tree or a type of forest or a type of rock. There's extra information in there, and it is an informed, you can say it's not just information classes, it's informed classes as well. Whereas the spectral class are just divisions of the spectral information. All the pixels are classed as having one type of color, as it were, or another type of color. Again, when I say color, I mean all of the parts of the spectrum that are measured or available to us. And this, by making this division, we create so-called spectral classes. What we would like is that for the spectral classes to have a one-to-one match to an information class. That would be ideal. That is very rarely the case, but we would at least hope that we can take a number of spectral classes and say, well, these are an information class. We create subclasses to say, well, this spectral class was this type of forest, and this spectral class was another type of forest, perhaps. Or this was another type of forest in shadow. We have to make these decisions. It's our job to inform the computer about what these different things mean and what we're trying to say here. There's no way the computer can really do it without our help. We can use specific libraries that say this is what this looks like, but most of the time we are actually analyzing the data that's in the image. So we look at the image here, say on this left, we have an aerial photograph, and we're looking for pixels that look roughly the same. We don't know what's emitting, or the computer doesn't know what's emitting the light. We can make a guess because, like I said, we have our big fancy brains that can look at the context of the color in here. But the computer is analyzing this pixel by pixel, and it's just looking at the light that's being emitted or reflected, mostly reflected, depending on what data we're looking at. But this, of course, there's not just the effects of the reflection do not just tell us about what's doing the reflecting. We also have the problem of illumination and shading. So if we have a sloping surface that's sloping towards, say, our receiver, the sensor, we might get a stronger signal. If it's sloping away, we get a weaker signal, just because the light is being sent in a different direction. We also might have a wet surface. Water absorbs light. This would be recognized, become darker. We can see that even here in this image. We have this wet field, and we have a river here, quite dark things. So this is a field just as much as this is a field, but this is dry and that's wet. So obviously we have issues to deal with there. We have to be able to take care of these. These end up becoming different spectral classes, even though in terms of information, we might think that they're the same thing. This is a field, the field is a field. Of course, we can turn around and say we create a subcategory whereby this is actually a wet field. This is our subclass. It's a field that is wet, or we have woodland that is in shadow here. It's still the same type of woodland, it just happens to be in shadow. If the sun were in a different position, that would be illuminated differently, but it would still be the same thing itself. It hasn't changed, just the illumination has changed. And so the signal that's being sent back up has changed. So this is this relationship between the information class and the spectral class. And we need to be able to inform the computer of this. And we need to be aware of this when we are instructing the computer what to do, regardless of how we proceed after this. So the reclassification from the spectral classes has to deal with this. Unfortunately, it may not be possible. When we look at a spectral class, it may consist of pixels that we just cannot uniquely identify as belonging to a particular information class. If we think back to the first GIS remote sensing course we did, we had to classify a satellite image, and many pixels were many of the classes were quite ambiguous. Was it road, or was it dry field? Were we in town or somewhere else? There were many pixels where in one part of the image it seemed quite obvious what the particular class was, and then when we looked somewhere else in the image, well, that class seemed to represent something else. It may be quite difficult. It's not always straightforward.